All right, so welcome. Here is the solve video for my non-consecutive Sudoku run free. The rules are standard non-consecutive rules, so you have the standard Sudoku rules, as well as orthogonally adjacent digits can't be consecutive. If you haven't encountered this constraint before, what it means is, for example, if I have a 1 here, well, can't have a 1 there. If I have 1 here, then I can't place a 2 here. And you can see FPuzzles helpfully makes that red, so we know we made a mistake. And so for any given cell, the 4 adjacent ones, up, down, left, and right, cannot be consecutive with that number. So 1 is special because 2 is the only consecutive number. But for example, with 5, we can't have a 4 or a 6 next to the 5. And that's the only rule. I've been doing a lot of research into this constraint, and this is the result. I'm going to go over the solve for this puzzle first, and then if you stick around to the end, I'll have some fun little extra details for you. All right, let's get started. I guess I should also mention there's one point in this puzzle where a lot of people get stuck, and I certainly don't blame them for doing so. It's particularly difficult at that point. What I'm going to do is for people who are stuck at that point, I'm going to solve till then. I'm going to give a couple hints, so you have a chance to pause and see if those hints help you, and then I'll move forward with the actual solve after those hints. All right, so the first thing we can do is notice that 3s can't be next to this 4, and also can't be in this row because of this 3. So this is the only place for a 3 in box 1. Similarly, 7 is blocked here from this 7, and is also blocked here because of this 6, and so 7 is here. These two 3s, we might as well corner mark some 3s here. Oops, 3s. Additionally, 7s can't be here, so we can corner mark these 7s. And next, this one's a bit fun. If you look closely here, what number can this be? Well, it can't be 1 or 2. It can't be 3 or 5 because of this 4. It can't be 6 or 8 because of the 7. And so the only remaining digit is the 9. And as a general rule, something you can look out for is if two numbers are sort of see the same cell adjacent to both of them, and they're far apart from each other, then you're going to restrict as many as 6 values. So there would only be up to 3 candidates for this cell, for example. So that's a nice thing to look out for when you're looking at solving consecutives. Something else we can notice here is that 4 is unavailable in that row because of this 4, but also there's a 3 here, which blocks a 4 from being here, and this 3 blocks a 4 from here and here. So this is the only spot in box 2 for a 4. Also, 4s can't be here, 4 can't be here, and this 3 prevents this from being a 4. So we can put a 4 right here. And also 7s are blocked here and here and here. These two 7s also prevent the 7 from going in column 9. So this is the only spot for a 7. Finally, I am going to pencil mark this row, or this column, sorry. And we'll discover something when we do so. So we can have a 3, we can have a 5, we can have a 6, or an 8. However, if once we've done that, we notice that none of these 3 can be 8s because of this 7 and this 9. And so this is the only spot in the column for an 8. And also because of this 7 here, we can't have a 6. Also, finally, looking at the center box, we have all these 7s converging, and so we can corner mark some 7s here. All right, so next we can focus a little bit on the top left again. So one thing we can see is that these 3s block 2s in this block box from being anywhere but the top of the box. Additionally, 5s can only go here. 5s, because you can see the 6 prevents those from being 5. And I'm just going to, these other 3 cells are fairly restricted, so I'm just going to mark what those can be. So this can't, for the entire box, we've got 1, 2, 5, 8, and 9 remaining. Can't be 1 because of the column. Can't be 2 because of our corner marks here. And can't be 5 because of the 6. So that's 8 or 9. And if we could get rid of the 8 or 9 candidate, that would certainly help us. This center one similarly is 1, 8, or 9 because it has the 2 restricted from the 3 and the 5 restricted from the 6. And this is 2, 8, or 9 because of the 1 restriction here and the 5 restriction from the 6. Additionally, I'm just going to point out that 1 can only be in these 3 squares. And finally, we can see this 4 here. Now that this 8 has been filled in, this 4 causes a 4 to be in this column here. We can see that this square cannot be a 2. Now, the reason for that is we have these 3 1s corner marked, which I just did. And this square sees both of these corner marked 1s. So either this square is a 1, in which case it's not a 2. 1 does not equal 2. I learned that on Cracking the Cryptic. And if this is not a 1, then one of these 2 has to be a 1. And whichever one is a 1, it sees this square, which means it can't be a 2. So in general, the rule is if you have 3 squares that are all adjacent in some way, so like this way, straight line, and the value is limited to being in just those 3 within some constraint, so say within the column, within the row, within the box, then the center one cannot be any of the 2 adjacent values to that. In this case, because it's a 1, it just can't be a 2. But say if these were all 2s, this square could not be a 1 or a 3. So we're going to use that rule and say this can't be 2, and we know these 2 can't be 2 because of the 3, and this can't be 2 because of my corner marks here. So this is the only square in the box that a 2 can be. The next thing we can do is look at this top row. So, or in general, where certain numbers can be in this box. So we already know 2s are limited to these 3. 5s are very limited because of the center 4, and that's always powerful. So if you have a center number on a box, that's going to limit 4 other squares in that box from being its adjacent numbers. So we already have a 3 placed, but we can look at 5. And we can see from this that 5 is also limited to the top. And then if we look at 6s, 6 can't be in this row, and 6 can't be, sorry, that's misclick. 6 can't be adjacent to this 7. And so 6 is also limited to the top, which means that we now have a triple. So this can be 2, 5, or 6. This can be 2 or 6. This can be 2, 5, or 6. But here's another trick. When you have a triple like this, and 2 of the numbers are adjacent, those 2 numbers can't be next to each other. We can't do like 6 and then 5, or 5 and then 6. I mean, 5 can't be here, but let's say we wanted to put a 5 here. We couldn't put a 6 anywhere. So what that means is the cell in the center of the triple has to be the odd man out. So we have to put the 2 here. And of course, I accidentally marked 6 up here, but there is a 7 next to it. And so now that we have this 2 marked, this has to be a 5, and this has to be 6. All right. So now it should be fairly simple to see that the 3 remaining numbers, one of which is 8, 8 can't be next to the 7. So this is the only spot for it in box 2. And then the remaining 2 numbers we have left are 1 and 9, which unfortunately we can't disambiguate yet. So now I'm going to go through the remaining cells in box 3 and box 6, and I'm just going to fill in the candidates because it is fairly limited at this point. So obviously I just looked at this, and this can be filled in. This is a 3 because we have the 5 in the row. So these 2 can't be 3. With these two not being 3, they're limited to 5 or 6, but I failed to notice this 4 here. So this is actually can only be 6, and this can be 5. I'm going to be doing that a lot where I miss some obvious stuff. Don't feel bad if you miss a consecutive. It's really hard to catch everything. So this top row, we have 1, 8, and 9 remaining to place. So 8 was placed here, so we have the 1, 9 pair. So the only two values left is a 2, 5 pair. And this can be 1, 6, 8, or 9. This is 1, 6, or 9. These two here. So the 4 values remaining in this box are 1, 2, 3, and 8. If we look at this 7, it prevents these two from being 8, which I'm going to immediately mark as there has to be an 8 here, which means I can remove this 8 pencil mark here. And then on the other side, we have a 4 that's preventing these from being 3, which means that I can corner mark 3s up here. Okay, so the next thing to see is that this is actually probably the strangest naked single you'll encounter. So how is it a naked single? Well, it obviously can't be 1 or 2. And because we have this trick that we actually saw earlier with these 1s, the center one can't be 3 or 5. It obviously cannot be 6 because it's next to the 7. It can't be 7. It can't be 8. And it can't be 9 because it's next to an 8. So that leaves 4. We can do that. Also, if we look at row 1, we can see that 1s are limited to the top 2, to the top row here. So these two can't be 1. So we can get rid of that. And we can also notice that 6 has to be down here. Might as well corner mark that. Okay, so now that we've placed that 4, that actually does something very interesting to column 7. And the question we can ask is, where does 5 go? Because we've now eliminated 5 from both of these squares. So, and 5 is already in this box, so it can't go here. And we can't put a 5 here because of this 4, and we can't put a 5 here because there's 1 in the row. So that leaves this square for a 5, and that's gonna break open the puzzle a little bit. So we have the 5 and the 2. The 1 can't be next to the 2, so this is a 9. That leaves this square for a 1. That makes this an 8. From the 9, we can now get this 6. And the final value is 8. Also, we place the 1 here, which actually makes this a 2, 3 pair, so I can remove my corner mark. And because that's a 2, 3 pair, these can't be 2. So we can remove that corner mark. And this is about as far as people get before you really have to start looking hard. I don't blame you if you got this far and then decided to watch my video. I probably would have done the same thing. So I'm going to start with a couple of hints. And then after I've given those hints, feel free to go back and try it if you feel like maybe that hint can help you. If not, or if you've given up, just keep watching and I will solve the rest. So the first hint I'd like to give you is to focus on box 5. So, and I mean hyper-focus, there's a lot of work to be done in and around box 5. And so I will give you a chance to pause. All right. If you've come back, my second hint is to really focus on column 6 and row 5, especially in relation to box 5 and its interaction with the things around it. And that would be the final hint. One last chance to pause, and I'm going to continue the solve. So first, I'm going to fill in a few squares that are actually much more restricted than you might initially expect them to be. So first, we can look at this square. And the reason I'm focusing on it is we do have these pencil-marked 7s. that means that this square can't be 6 or 8. And we can see that it has a lot of restrictions that aren't 6 or 8 in addition to that. So it can't be a 1, can't be a 2. It can be a 3. 4s are restricted, 5s are not restricted. We already said 6, 7, and 8 are restricted. And it can't be 9 because of the row. So this is actually a 3 or a 5. This square is similarly restricted, so we can't be a 1. We can be a 2. 3, 4, can be 5. It can't be 6, 7, or 8 because of this 7. And it can't be 9. So this is a 2 or a 5. And finally, these two are a little bit less restricted. They have 3 candidates each. And I will explain why, because that might be a little harder to see. So first, we can be a 1 in this square. We cannot be a 2 because of the 3. Can't be a 3 or 4. We can be a 5. And then we got 6 restricted, 7 because of the box, pencil marks. 8 is restricted, but we can be a 9. In this square, again, we can be 1. Let's just for now say we can be 2 and 3, and I'll go back to that in a second. We can also be 4, but we cannot be 5, 6, 7, 8, but we can be 9. Now I said I'd come back to the 2, 3. Now this is another trick that I haven't shown yet, which is going to come up a lot in non-consecutive constraints, which is we have one square that's limited to 2 values that are consecutive. So this is going to be a 2 or a 3. So the question we can ask is, can this square be a 2 or a 3? And the answer is no. If it were 2, then this can't be a 2 because of, obviously, the row. And it can't be a 3 because it would be adjacent to a 2. It also can't be a 3 for the exact same reason. It can't be a 3 because it would eliminate the 3 and the 2 from this square. You can kind of think about it the other way around, which is this square is going to prevent any of its adjacent squares from being either of its values, because it's going to, whatever value it ends up being, say it ends up being a 2, that obviously removes a 2 from these because of Sudoku rules, but it also removes a 3 from these because of the consecutive rule. And if it were a 3, then the same thing happens, where these can't be a 3 because of Sudoku rules, and it can't be a 2 because of consecutive rules. So I can remove 2 and 3 from this square. I'm sorry if that explanation was a bit long-winded, but I think it's a really important trick to remember as you solve non-consecutives. All right, and so now the next thing that we want to notice is this square actually can't be a 1 either. And the reason for that is, let's look at where 2 can be in this column. Obviously it can't be here. We restricted 2 from here because of this 3. We restricted 2 from here because of this 2, 3. This square can be 2. And I don't know, maybe I should color that. So these 2 can be 2. And then this one can't be 2 because of the 2 in the row. So 2 is restricted to these 2. And that's exactly the same as this 7 here, where in this column, either a 2 is going to be here or a 2 is going to be here, which means this guy can't be 1, because either way it will be adjacent to a 2. So I can just remove this highlight now. Now, this square can't be a 5. And actually, 5s we're going to find are limited to these 2 squares. And the reason for that is, imagine if the 5 was somewhere else in this box. If it was, say here, then that would eliminate 5 as a candidate for here and here, which means we must place 3 and 2 here, but that would break the puzzle. We can't place a 3 and a 2 here. So this is another fun rule that you can spot, which is you have 2 consecutive squares, 2 adjacent squares, and they both are down to the same value plus 2 consecutive values. So it's kind of like a pair if you consider consecutives to be part of the pair. I don't know if that's a good way to put it. I'm sure there's a name for this and I just don't know it. But the basic idea is that if I were to put a 5 anywhere else, then it would cause a consecutive to happen. So all of that to say 5 has to be here, so 5 can't be here. All right. So we're slowly whittling down what the possibilities are in this box. All right. So now we can do something very similar here. Notice we have two squares. They aren't adjacent in this case, but they are both adjacent to the same square. And you might actually be seeing this now, after having explained this forever, which is, imagine if neither of these was 9. Well, then I must have 1, 4. Like that. Well, then what can this square be? It can't be a 2 because of the 1. It can't be a 5 because of the 4. So the only other option is one of these has to be a 9. So that's going to remove 9 as a possibility from all the rest of these squares in the box, as well as from the column. Now the next thing that we can actually do is we can fill in these two squares. So imagine what would happen if this was a 2, and therefore this was a 3. Well, the 2 eliminates the 1, making this a 9, and the 3 eliminates the 4, making this, you guessed it, also a 9. Well, we can't put two 9s in the same box, so that means this has to be 3 and 2. Okay, so the next thing I'm going to do is fill in the candidates for this square. So it can be a 1. It can't be a 2, 3, 4, 5, because the corner marks. 6, can be 7, can be 8, and can't be 9 because we corner marked these. So 1, 7, or 8. However, what would happen if this value were an 8? Well, if I put an 8 here, then now this square can't be a 9. So it has to be a 1. But then what can this square be? Well, it's got no candidates left, so we've hit a contradiction. So this is, again, something that's a bit difficult to spot. But I suppose what you can look for, again, is these pairs that share a number. We need to make sure that if we eliminate one of the candidates, then we're not also eliminating the other possibility in this square. So this can't be 8. Now we're down to 1 and 7. Okay, so next I'm going to fill in the rest of this column because we actually have some interesting behavior here. So just for the column, we need, and I'll eliminate the consecutives in a second, but for the column we need 1, 2, 4, 5, and 9. So we can see that this square can't be 1, this square can't be 2. 9 is eliminated because of the pencil marks. So now we're down to 2, 4, 5, and 1, 4, 5. Now if we look closely here, what happens if this square is a 4? Well, it eliminates the 5 from here, and it eliminates the 4 and the 5 from here. So just to visualize that, if this is a 4, this now has to be a 2, and this also has to be a 2. Well, that's not going to work. Can't have two 2s in a column. So this is not a 4, it is a 9. And that is going to crack open the rest of the puzzle. And I'm just going to fill in all sorts of happy things. So this can't be a 2 because it's next to a 1, so that's a 5, that's a 3. This can't be a 7 anymore. This is no longer 5s, this is no longer a 1, so this is actually 4 and 2. And we can actually fill in the rest of this box if we look carefully. So where can 2 go? Well, it can't go in the bottom row because of the 2, and it can't go next to the 3, so 2 goes here. We've got 8, 4, and 6. And these 2 can't be 4 because of the 3. So this one's 4. And then this one can't be 8 because of the 9, so we have, 6 and 8. Alright, from this point we've basically broken the back of the puzzle. The rest is pretty straightforward. I'll try to do it as directly as I can. So this has to be 4, 5, 9. This has to be 2, 6, but this one can't be a 2, so that's 6 and 2. And this has to be 3, 7, 8. Now the 4 and the 5 have to be split by a 9, so that gives us a 9. This 4, 5 eliminates 5 as a candidate here, so this has to be a 5. And the 9 means this is 1, this is 9, this is 1, this is 9. Same here, 3, 7, 8. This has to be a 3. And this can't be an 8, so this is a 7, and this is an 8. This is a 6, 9. And this is a 3, 5, 7 triple. Can't be 7, can't be 3. This column, the remaining are 5, 8, and 9. This can't be 5. This can't be 8. And this can't be 5. So we have an 8, 9 pair. So this is the only place for a 5. And the remaining for this column is 1, 3, 6. So this can't be a 6 because it's next to the 5. This can't be a 3 because it's next to the 4. Can't be a 1 because of the row. So this is 6. Leaves a 1, 3 pair. 6 gives us 9, 6, 8, 9. We can fill in the candidates for this row, which is 3, 4, 5, and 7. This can't be 7, this can't be 3, this can't be 7. And then from the columns, this can't be 4 or 5, so we place the 7. So that places the 7 here. That places this 3, and this 5. This is 1 and 3. So that's what I was missing. Sorry. And we've got 2, 6, and 9. I'm just going to fill these and then I'll reduce it. And this is 1, 5, and 8. So this can't be 8. This can't be 5 or 1, so here's our 8. And this can't be 1, so we have 5, 1. So now this can't be 2 or 9, so we got 6, 2, 9. These can't be 5s. This can't be a 3, so here we go. 4, 5, 4, and 3. And that's it. That is the run-free puzzle. So now I did promise some nice tidbits at the end. So the first thing I want to point out is this puzzle was specifically designed to have no ropes. And because it has no ropes, that's why I named it Run Free. I'm very clever. Obviously, I couldn't tell you from the onset that there were no ropes because that might have made it easier to solve, and there was no reason to do so. What is a rope, for those who don't know? Well, if you do a lot of non-consecutive Sudokus, you start to notice this phenomenon where, say, this is 8, 4, 7, and then for the other two boxes in this area, you'd have 8, 4, 7, then you might have like 4, 7, 8, and then here you'd have 7, 4, 8. Or something like that. So you'd have the same triplets like that. And then here you'd have 6, 1, 3. And then you'd have 1, 6, 3. And then you'd have like 3, 1, 6 or something. So, and then that would repeat where you have the same triplets all on these rows. Or maybe you'd have the triplets on the columns instead. Or there might be a mix where, say, that this has rows and then this has, columns. Or sorry, this has columns or something like that. And there were even puzzles where you have triplets on the ropes on the rows and you have ropes on the columns. So this puzzle has 0 ropes on rows or columns anywhere. So if there's an 8, 4, 7, there's not a single permutation of 8, 4, 7 in any other box row. So if we look for, say, 8, 4, we've got an 8, 4, 3, but we're not going to see that there's a row with 8, 4, 7. There might be an 847 column. I mean, I don't know if it's avoidable to have it nowhere like that. Probably not. And then also for columns, there are no ropes. So this 862, there will be no other 862s in this puzzle. The second thing, if you will allow me to... Actually, I'm just going to duplicate the tab so we don't lose our solution here. If I go into setting mode, this puzzle has a unique solution without this 1. It has a unique solution without this 7. It has a unique solution, in fact, with just these 4 givens. Don't ask me to solve it for you, because only a computer seems to be able to solve it, which is why I added additional numbers to try to make the puzzle difficult, but not impossible. So, again, if I were to flip back and forth here, you can see that I actually added more givens than were originally in the unique solution, or sorry, the unique setup. But I tried to do it in such a way that it would make a nice solve for a person. A computer has to make a significant number of guesses in order to get the correct solution here. So lots of bifurcation. But that is an interesting tidbit. And if you want, you can try to make your own puzzle by starting with these 4 and see if you can make a more interesting route. I have lots of these. You can contact me if you're interested in your own solved board with 4 givens. I might make more of these in the future. So that is a fun tidbit for you. Finally, since we were talking about ropes, I did do a interesting study. Non-consecutives are extremely limited. You may or may not be aware for classic Sudoku that there are a large number of possible solved boards for classic Sudoku. On the order of 10 to the 26, if I'm remembering correctly. It's incredible the number of solutions. Now, people have kind of reduced that by finding symmetries. So, for example, the easiest symmetry to understand is with classic Sudoku, the numbers don't actually matter. They're just symbols because they don't interact with other different numbers. Like a 1 is never going to affect a 2 directly with the rule set. And so you can swap the 1s and 2s and you have another puzzle. So there's actually 9 factorial permutations of what one might consider the same puzzle. You can also rotate the puzzle. So instead of 8, 4, 7, 5, 2, 6 this way, it would be 8, 4, 7, 5, 2, 6 this way. Or you can rotate it so 8, 4, 7, 5, 2, 6 is this way. Or you can just mirror it so it's 8, 4, 7, 5, 2, 6 this way. Or you can mirror it and rotate it. And so that ends up with a factor of 8 for mirrors and rotations. And then if you look at the wiki page on Sudoku, the mathematics of Sudoku, actually, there's even more symmetries that people have found. But even so, there are a significant number of solutions. Now, non-consecutive has far fewer symmetries. First of all, the only number replacement you can do is a 10 minus n substitution, which means 1s become 9s, 2s become 8s, 3s become 7s, etc. That preserves the consecutive nature of the puzzle. If you were to say swap 1s and 3s, then now, this 4 would be consecutive with a 3. That's not a valid puzzle anymore. And so the number of possible solved boards, and this is not including symmetries, so even including all the rotations and reflections and the 10 minus n symmetries, is just around 5 million. It's a bit over 5 million. So that just shows you how restrictive it is. 5 million versus 10 to the 26 is quite the difference. Even if we can't count the fact that we can't have the 9 factorial symmetry. So with that, you end up with the kinds of restrictions that we're able to find. And with 5 million, it is absolutely possible to find all 5 million of them and put them in one file. So by doing so, I was able to do a lot of analysis that normally you couldn't do on something like all Sudoku classic solutions. And so I did statistics and I found ropes. And if you were to come up with a random valid non-consecutive Sudoku, you would have ropes on either all the rows or all the columns, all the way down like that, right? With all of the columns having ropes and all the rows having ropes 70% of the time, which explains why it's so common. In 3% of the time, you're gonna within that 70%, you're gonna have it on both rows and columns. Of those remaining 30%, most of them are mostly roped. I don't have the statistics on that, but you might say be roped on the top 3 boxes, but not roped elsewhere, for example. In order to have completely unroped, there are, I believe, 32 puzzles. So I took one of those 32 to be my solution board, and then I used a computer to search for the minimum number of givens, which ended up being this. And then from there, I constructed this puzzle. So that's how the sausage is made. I hope you enjoyed that and found it interesting. I'll be sure to, if people liked this, I'll be sure to make more videos in the future of stuff I've set. I'm definitely still interested in researching non-consecutive. I'm especially interested in what I'd like to call spooky action out of distance, sort of taken on the quantum mechanics thing, where how can these givens possibly affect, the far away boxes, right? How does that restrict this box? That's kind of really difficult to see, and logical solvers aren't able to get very far on puzzles like this. And so is there some sort of weird hidden technique that'll blow open non-consecutives and make, stuff like my puzzles super easy? I'm very interested in doing more research into that. I can't guarantee I'll get any results, but yeah, stay tuned and stay safe.